Good morning, everyone. Welcome to this wonderful session as I announced on the plane. This is on promoting early math advances and understanding who to teach what. If this is not the flight that you're on, this is your last chance to leave. So you guys chose a wonderful presentation to come to this morning. I'm Darryl Greenfield from the University of Miami, and I do research on science. And for those of you that have been paying attention to recent interests in early childhood, STEM, science, technology, engineering, and math, have been a topic that is getting increasing interest in early childhood, and it's for good reason, because these topics, which originally were thought of as too advanced for young children, are things that not only are not too advanced for young children, but these are what young children are most interested in. They're trying to understand how their world works. They want to quantify their world. They're involved in technology. They love to build things. And these are the features of STEM, science, technology, engineering, and math. And the STEM acronym, they spent some time thinking about how to put that together. And they put science in the beginning and math in the end, because those, in some sense, are the anchors and the bookmarks for this new area of research. One of the difficulties we're having is that our workforce is not really well trained for STEM. So even though children are excited about the STEM and are doing it in classrooms, the teachers and the workforce are not prepared for this. And what we really require is a roadmap and an agenda for how to do this. Now, we're extremely fortunate in that Doug and Julie have been working in the math area, and they have really created a marvelous roadmap that really has been thoughtful about a wonderful research agenda, how this impacts practitioners. So they've been thinking about not just the research as pure research, but how it applies in the field, and also implications for policy. So the STEM area, which science is just starting, technology and engineering, there's not very much going on, but there's a lot of interest in it. Math is the area where we really have this wonderful roadmap to follow, and it's largely due to these two wonderful scholars. I'm not going to spend a lot of time going over their bio, because I want to spend as much time as possible having you hear them talk, but if you look at their bio, you notice they both have endowed chairs. Prestigious endowed chairs, University of Denver. They're professors. They have a long history of important research, again, as I said, that has both policy and practical implications. So it's my great pleasure to introduce my colleagues and friends, Doug Clements and Julie Sarama.
I'm just going to start off by just telling you a little bit about what we're going to do today. First of all, We're married, and our style of presenting is fairly fluid. I like to think of it as a highly coordinated dance over who does what slides, but mostly I think then that dance is really looking like what my son's an escort for a quinceañera coming up, so I'm watching them practice that dance, and I have a feeling that that's more what we look like, where they end up looking at each other a lot like, no you. So that's probably what we're going to look like today. But if we interrupt each other, it's just because that's the way we'd like to think about it. So we are going to talk about early math and the surprising importance and delve into research. Again, we're going to violate one of the key principles, which is come away with 3 important things, because when Darryl asked us for what we were going to do, Doug wrote down like 12 things, and Darryl said, great. So we're going to go with that. So, all right, Doug, you want to start?
Yeah, so let me start off with the first thing, which is we need better math. And if you aren't convinced by what Darryl said already about STEM and the like, maybe these advertisements will convince you, right? Buy 3 for the price of 3. Really? Now, if that doesn't bring them into the stores, everybody loves a sale, right? So let's check out this sale. Get 50% off or half price. You pick. So I guess they want you to compute both of those and compare them or something. And we don't do a heck of a lot with statistics in early childhood. But you know, statistics is in trouble if you can read that statistics definitively show that teen pregnancy falls off after age 25. Okay, I can see why that would happen, right? So we're going to talk about what's surprising about early math. It's not surprising that we need more STEM, like Daryl pointed out, but what is surprising about early math? Well, first of all, it's predictive power. You may have heard this. Greg Duncan's been working now for a decade on these kind of large-scale research where he looks at and I hope you can read those from left to right. It's reading, then math, then attention, internalizing, externalizing problems, and then social skills. And the closer those are to the horizontal bar there, the more the prediction is near zero, right, of early. But the most predictive one of all those was mathematics. Daryl, they didn't get science at all in there, showing lack of intuition on these people that designed the database. We got to tenor that, though, because some recent research, one study that we participated in with Greg and Drew Bailey and another paper they write, shows that latent trait effects on kids' math development substantially larger than state effects. In other words, if you just run these correlations, it's just straightforward, so what correlates the most? But if you look at experimental evidence, like our own triad data that we're talking about later, it turns out that a large part of what we're fighting when we try to help kids from low-resource community, kids that don't come in with a lot of advantages, are these kind of stable trait effects, the environment they're in, the resources they have, and everything. So you got to be careful with the correlational evidence, but it does mean we need continuous, not just early childhood, but continuous high-quality education. Okay, that's surprise number one. Surprise number two is children's math potential. Young children can learn an amazingly broad, complex, and sophisticated mathematics. I was on President Bush's National Math Panel, and we concluded most children acquire considerable knowledge of mathematics before kindergarten, and, like the Duncan studies, it's related to their mathematics for years thereafter, to high school, to predicting college entry, right? But let's take a look at what that looks like in preschool, right? So here are some kids that have been through Julie and my Building Blocks program, but they just pulled this wooden puzzle off the shelf there. And Corey's putting 4 triangles, actually triangular prisms, together, puts them in the puzzle. 4 more, puts them in the puzzle. 2 more boys come along and want to do it. Well, let's see what Corey's doing first. If you can't see the puzzle, he's going like that, right? So this other boy wants to join, and he makes a square, but he makes it out of 2 triangles. It doesn't fit. The boys have this long discussion. Finally come up with, oh, you got to do it this way to make it fit in the puzzle. Finish the puzzle. They show the adult, the teacher there, who says, how many triangles did you use? And Corey counts 1, 2, 3, 4, 5, 6, all the way up to 24. Good counting for a preschooler, right? And then his teacher doesn't stop there. 24 what? Triangles, he says. And she saw how they made it, so her next question was, how many squares do you have? And this is where Julie and I get really interested, because what Corey does is curl up one little finger, leaving 4 fingers down, puts them on each of the 4 triangles of a square, and counts 1, 2, 3, 4, 5, 6. So it's great that he can count. It's great that he can put shapes together to make other shapes. It's fantastic that he can make units of units in the geometric and numerical sphere. What do I mean by that? He can see the individual triangles as countable, but also count them as a group. He can see the triangles as separate and also can see them together as a square. 2nd grade, these kids do double-digit addition, subtraction. They're already thinking, how do you put things in a group? So when they have to think of 10 ones as 10 separate ones and 1 10 and go back and forth between those conceptualizations, they have the foundation already at 4 years of age. Oh, Julie, I should have started that, actually.
That's okay.
No, let me stop it.
See, here we are, exactly. You promised we wouldn't do this, but here.
So soon.
So let's just watch this little girl and how she's a 4-year-old. She's solving a problem. I'm actually interviewing her. How much is 9 take away 4? And let's listen to what she does.
5.
Good. How do you know?
I know that 4 and 4 is 8. So when I think of 9, I know that there's 1 more. So if I take away 4, it's like take away 4 from 8. So if there's 1 more still hanging down, I'll put that on. That's 5.
Good.
So she's obviously thinking about number in a much more advanced way than most people think 4-year-olds can think. And so what happens? What do most adults think? Well, in the Netherlands, they asked teachers and like their coaches and their administrators, lots of adults that work with these young children, how do kids do on these things? And so they said, first of all, how about counting? Can they count 2 marbles, 5 marbles, 7 marbles, 9 marbles? And what you see right there is how well children did just doing simple counting. And how did the adults in their life think they did? Not as well. I think the adults thought they could do the 2 marbles, but really that most adults highly underestimated how well children could count 9 marbles. Go again. How about some harder stuff? There we go. Adding or subtracting within a context. So, when I had asked Abby, what's 9 take away 4, that was without a context. So this is within a context. So these are the simple problems: 5 plus 1, 2 plus 4, 1 plus 3. Sometimes they had objects to count, sometimes they didn't. And as you can see, the black bar, what the children could do. And you know what? As it got harder, the kids didn't do as well. Like 50% for the hardest subtraction problem. But the adults thought nobody would get it right. They had no idea. So what happens? So the next surprise? It's a surprise to educators. What young children learn and what they can learn is a surprise. Therefore, they don't challenge or use formative assessments effectively. So what happens when a kid like Abby starts preschool or starts kindergarten? She gets a little gold star on whatever they tell her to do, but whatever they tell her to do is going to be probably way beneath what she's ready for. And that happens to too many children in all contexts.
But it's surprising how many kids benefit from a more considered math education, a more intentional math education. This is not our research. This comes from Steve Burnett et al., right? So what you're looking at there is the tall horizontal line, right, is just the upper quintile of SES, those that have the top fifth that have the most resources at home, right? And notice the gap in everyday kind of concepts, which include a lot of science that Daryl was talking about, as well as then other kind of things, and reading and mathematics. The gap grows as kids have less resources, for sure, but the gap is there and significant at every level other than the top. So, surprise number 5 is we know a lot. We know a lot about how children think and learn math. We know a lot about research and development to do these things well. So Julie and I just want to introduce, I'm going to do a whirlwind tour through this because it's not the main point of our presentation, but we created what we call the Curriculum Research Framework. And we would like to emphasize that this is what we think research and development should be when you approach something like what should be our standards, our curriculum, our teaching practices, and the like. We think any comprehensive program of research and development should answer 2 kinds of questions, effects and conditions, for 3 groups of interested parties: practice, policy, and theory, right? So for instance, the effect. In practice, you want to know, hey, is this going to achieve my learning goals? For policy, what exactly is the effect size? Which do I choose? Are these curriculum goals important to me? And for theory, why is it effective? Why is it credible relative to other alternatives? For conditions, for practice, where and when is this going to work for me? With whom? Policy, how do I support this kind of thing for teachers? What am I going to need to do to make this work? And for theory, why do certain conditions increase the effects? How and why do strategies produce previously unobtained results? So our curriculum research framework tries to answer those 6 type of questions by going through 10 phases in 3 broad categories. And this is what we did when we created the kind of materials that you'll see in the rest of the presentation, right? First, review the research. Many people do this, but it's an important beginning. What are the broad philosophies, theories, and empirical results that guide your curriculum? What do you know from research about the support for those? Rather than just saying, oh, I believe in play, or I believe in this, or I believe in that. What's the evidence? Subject matter. You better know what's important. In STEM, what are the important scientific ideas for kids to bring up? In mathematics, what are things that are not only achievable for kids, but build a foundation for their later learning? And finally, pedagogically, what are the strategies? What are the teaching strategies? Should it be center? Should it be small group, whole group? Should we use technology or not? And the next thing we do, and this takes 90% of all the time of this development kind of thing, is learning trajectories.
So what is a learning trajectory? I'm sure people have maybe heard the term bandied about a bit, and I think the biggest thing that happens with me when I talk about learning trajectories is some people say, well, I like to think about progressions. I like to think about learning progressions, or I like to think about paths and learning paths, and are all these things the same? Well, for us, they really aren't the same. A learning trajectory has three main parts: a goal, a progression, and the instructional activities that get you there. What does that mean? Well, when I talk to teachers, I try to explain it like this. In math, there are several goals. So imagine you're in a garden, and it's a really, really big garden, and there's all these, there's different points at the other side of the garden that you want to get to, and those are your goals. And there are different paths then that get you to those goals, and those are nice stepping stones, spaced pretty far apart. And that is a developmental progression. We know from lots of research that lots of people have done, from cognitive psychology, developmental psychology, from math ed research. We have an idea of how kids learn these math concepts. There's already a lot of research. And that forms the idea of what comes next, what's the next stone. And then finally, the instruction is very important. It tells us, how do I get from one stone to the other? So the teachers will say, that's great, so I have a child who's here. I have Abby, and she's doing this. How do I meet her needs? Well, first of all, we have to figure out where is she along this path, and then the instruction piece says, oh, for someone like her, let's try one that she's coming up using former combinations, like 4 and 4 is 8, and adding one more. Let's try stretching that and adding slightly bigger numbers, or let's try doing these next kind of problems where she is an unknown beginning or an unknown end. And that's the next step on her garden path. So really teaching teachers that is fundamental to our approach. And go ahead. So in counting, let's just take counting as an example. What's our goal? Clearly we want children to be able to count. We want them to be able to count probably a large number of objects with understanding and be able to understand what's one less and one more and things like that. What's the developmental progression look like? Let's take a look at that. Just see what do those steps look like. So let's start off with verbal counting. Verbal counting is really important, right? If you don't know the number words, you can't get very far. And because we work in all kinds of settings, we've met children who have entered preschool who don't know any number words. And in fact, will pull off random words but know something that they have to point, watching their friends point, and they'll say some other words or just make some audible sound. They know they're supposed to do something, so produce some speech, but not really know the number words. So just knowing that there are number words, we consider that, all right, you've got it. And those are the kids who say number words, but they're not in any really significant order. They just say number words. 4, 23, 8, some number words. Next, we have chanters. Chanters start knowing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's elemental P. It's my country 'tis a thee. That's one, right? It's one long word. Those are chanters. They can't start and stop again. Therefore, they can't really use it to break down and attach each singular word to an object. Finally, there are reciters, where they really are verbally counting. Each word has a specific meaning, and they first get to be about 5, and then they do up to 10. So let's watch, and this video has made the rounds on Facebook. I think it has 3 million views, so probably some of you have seen it. But I want you to think about it in this way. We all saw it as a strong-willed child, cute interaction between daddy and daughter. When I watched it, I thought, first of all, what level is she? And what's the instruction? So go ahead, Doug.
4, 5.
No, it's 1, 2, 3, 5.
No, 1, 2, 3, 4, 5.
No, 1, 2, 3, 5.
No, it's 1, 2, 3, 4, 5.
No, that's 1, 2, 3, 5.
No, it's not 1, 2, 3, 5. It's 1, 2, 3, 4, 5.
No, that's 1, 2, 3,
How you gonna
5.
tell me? How you gonna tell me? I teach this every day. It's 1, 2, 3, 4, 5.
No. It's 1, 2, 3, 5.
No, it's not, Aaliyah. It's 1, 2, 3, 4, 5.
No. It's 1, 2, 3, 5.
No, sweetie. It's 1, 2, 3, 4.
No.
5.
It's 1, 2, 3, 5.
No. No. It's 1, 2, 3, 4, 5.
No. It's 1, 2, 3, 5.
Aaliyah, it's 1, 2, 3, 4.
No, Mommy. That's 1, 2, 3, 5.
No, you're skipping 4.
You're skipping 4. You can't just leave 4 out. It's 1, 2, 3, 4, 5.
No. It's 1, 2, 3, 5.
No, that's not right. It's 1, 2, 3, 4, 5.
No. That's 1, 2, 3, 5.
Aaliyah, I'm not gonna keep going back and forth with you. It's 1, 2, 3, 4, 5. Yes.
Yeah. Count to
1, 2, 3, 5, Mommy. It's 1, 2, 3, 5.
It's 1, 2, 3, 4.
No, Mommy. It's 1, 2, 3, 5.
All right, count to 4.
1, 2, 3, 4.
Yeah. You did it.
Okay.
What?
Point proven.
So,
7,
Yeah.
yay! So clearly she's between a chanter and a reciter, where she's really understanding these number words. She doesn't have them all in order, so she's getting there. But to me, the really important thing was, the dad could be, still talking to her in that parking lot, right? She wasn't going to give an inch. The way to get kids to the next path is not to tell them what's true, right? The way to get them, but the mother offered exactly the right instruction.
I knew you'd bring that up.
Yeah.
What did she do, though? Seriously, what
No.
did she do that was so smart?
What was so smart, she asked her to count to 4, right? And then that got her out of that mindset. It stopped and said, I have a new task to do. 1, 2, 3, 4. And then she was happy. Little celebration. She felt the need to keep going because 5's clearly really important for her right now. But that's what and so if we teach teachers this and we explain to them where kids are developmentally, then when we do counting activities, doing counting with the calendar makes no sense, because we say the calendar is determining what number you're stopping at, and that might not be where your children are. So if I had quite a few Aaliyahs in my class, we would be stopping at 4, because stopping at 5 would be a bad thing. That last number word has, ascendance, right? So we want to stop at the number they're having difficulty. Lots of times in preschool classroom that happens to be the early teens, right? 13, 14, and 15 are the ones they miss up all the time. And so having teachers stop at that number is really important. Also, it's not rote. Let's check out this girl, Doug. I know what happened there.
Oh, somehow I canceled. Sorry about that. No, I got to go back. There you go. My fault.
Please
That's my fault.
count as high as you can.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. What comes after 3? I know, 4. 41, 42,
Okay.
43.
So it's not rote. Some people call it rote counting, but it's not rote, right? So she knows the system. She knows it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I need the next 10 word. Help me out here. And she knows that the next 10 word is based on the 1, 2, 3, 4, which is phenomenal, right? So she knows 3 maps to 30, 4 maps to 40. So 39, 4, 40. Go ahead.
It's not until 4th grade that the majority of U.S. students understand that 50 and 5 have a relationship.
Right.
4th grade, because nobody talked to them. Somebody talked to this girl about it. Somebody dealt with that. It's not as rote counting, but it's a pattern structured
Right.
system.
So we don't call it rote counting, we call it verbal counting.
Do you want to
All right.
introduce this one or no?
Well, this next one, let's just look at this little girl and see how she counts objects, moving beyond verbal counting now. Let's see what she does.
1, 2, 3, 4, 5, 6, 7, 8, 9, 3, 4, 5, 6.
All right. Thank you very much.
So again, let's look at her strengths, right? She knows some number words. She knows some number words in a sequence. She knows she's supposed to point to objects while saying a number word. She really, though, still doesn't have that one-to-one correspondence that we would like to see.
She doesn't have a conceptual idea that that one-to-one correspondence must be maintained for a reason. So it's just, I'm supposed to count, but look what's interesting over there.
Yeah, and then at the end, when I run out of counting words, I'm going to go back to some I know and I like. So, okay, go ahead. Compare her to this little girl.
Would you count these for me? How many chips are there all together?
Now compare her
Thank you.
to this little girl.
1, 2, 3, 4, 5.
How many?
5.
Okay. So do you see the difference there? So that middle girl was able to keep one-to-one correspondence, and at least for a set of objects that were 5 or less in a row. So we would call her a corresponder. But she wasn't a counter small number, but that last girl was. Why? Because that last girl had cardinality. That last girl was able to say that that last number word told how many. This is something that most preschool teachers don't understand. So therefore, they don't ask kids how many. The kids go 1, 2, 3, 4, 5, and they think they're done. And when I talk to teachers, and we do talk to teachers all over the country in various contexts, many of them will say, well, she just forgot, or she didn't know, or she didn't whatever, and really not understanding that it's a conceptual leap. These are different stones along the path, and we need to keep focusing on understanding that that last number word tells how many. That second girl really didn't understand that 5 is the 5-ness. 5 is the number of that last guy. And if we said, give me 5, she's just as likely to give me the last chip, because that is 5. Let's check another little kid who's about the same level.
1, 2, 3, 4, 5.
He's asked to put 6 bananas in a cart.
5.
5 bananas in a cart, there we go. I guess that was 6.
1, 2, 3, 4, 5.
Yeah, 5. Take one out and put it at the end.
1, 2, 3, 4, 5. There's only one more. You're missing it.
I messed him up.
1, 2, 3, 4.
Okay. All right.
No,
I
little
keep
more.
missing them.
Well, what can you do?
I can sabotage.
Take some off. That'll work.
1, 2, 3, 4, 5. 5.
I got it. Oh no! He's putting the bananas back.
Yeah. When they're at a level, sometimes it can be a little difficult to move. But that was actually an assessment of this child. It wouldn't
All
be
of
something.
these have been
All
assessments.
have been assessment tests. They're not activities that we do with kids. It's just assessment that we would use along the line. And it isn't the key, isn't the instruction. But that child is a counter small number, but he's not a producer. Right? He is not able to stop at the appropriate amount. Clearly, he can count. He knows 5. He knows he's too many. He just can't produce a certain set. And so then what do we do? What do we do for kids at all these stages? Because clearly, they're all in my classroom, right? We want to teach teachers how to do that. And that's where we go to the
So
instructional
the first
activities.
task corresponder.
Go ahead. So we can do some things, this is just an example. We do lots of activities both on and off computer. The computer activities actually are very small. They take about 10 minutes a week. But in this case, all a child does is click on an object, and when he clicks on it, it says the number word.
3, 5, 4.
Do you see how the computer, he took the computer's correction to his verbal counting, but that didn't take him off his game, which was concentrate on one skill that he needs help with.
Right, so that's just building up that one-to-one correspondence. There's no way to quickly click on all the apples, and every time it's slow, it's methodical, makes you maintain one-to-one correspondence.
Talk about small numbers, too, for the next task.
Why don't you talk about small numbers, too? All right, so
here we go.
So here's...
Two. Okay, can you both put 2 chips on your cookie?
So this is, you can start off games, and we're going to show this at multiple levels, with really small numbers, which gives you an access point to almost everybody.
2.
How many is that? Okay, can you help Bobby?
You need to take one off. Like, that's not 2.
Good job.
One, not the other one. That's 2. Like 1, 2.
All right, you both got it. Let's try again. Put your chips.
So there's a few things going on there. One is that they are using a very small number because those kids clearly that little boy is a little farther back on that path. But the teacher is able to quickly change what she asks the girl compared to what she asks the boy, even within that little dyad. And usually people work in small groups of about 4 children, so it's easy to put them in pairs and to separate what numbers you're working on. Secondly, it is that this is accessible to kids, that game is accessible to children who are really just learning counting. And third,
Thank God there's women around to correct men's mistakes.
exactly. It's a very important lesson that we use to show
No,
teachers.
no. Kids can help each other,
Kids can
regardless
help
of
each
gender.
other.
That's
Yeah.
the main
No,
point,
no,
right?
no.
How about this game?
So that was a beginning example of something that eventually turns into cookie game. So in cookie game, kids, it's a cookie or a pizza depending on where teachers are using it and how strict people are about nutritional guidelines. So this is an older version of the game, and we'll do cookie instead of putting toppings, mushrooms on pizza. So kids roll a die. So they roll a die in this case. They get 4. They take 4 out of their little basket. They put it on a plate, and they turn to their partner and they say, "Am I right?"
Yes, you are.
Thank you. And then I am able to put them on my cookie. And then it's my partner's turn. They roll the die, and it goes on. So why is this a good game? Well, next slide. First of all, there is this partner piece, which is a nice thing for self-regulation. It gives us both something to do, and it's not just being a good turn taker. I actually have a role. Yes. So he said, "Am I right? Am I right?" Kid's not paying attention. "Am I right?" "Yes." "All right, good." And I can move on. But secondly, there are multiple goals for the math, right? And you can adjust it based on kids' abilities, really in a group kind of setting. So go ahead. What are the goals? Lots and lots of goals. You have to make small collections. You have to count by 1s to 10. You have to have cardinality. To know the last counting word tells how many, at least if the sets are more than 2, because that little boy could probably do it just by understanding and knowing 2. You have to be able to produce the set. You have to quickly sometimes see, so if you see 2, you just get 2, you know 2, that's called subitizing. And as the partner, you have to be able to compare, to identify which collections are the same. Right? So if the partner did it wrong, you have to be able to say. So it's one simple game, lots of goals. So for people who are like, oh, isn't that sort of a reductionistic kind of approach if you're using learning trajectories where you're doing one step and then the other and then the other? Not really. You can have multiple goals and continually be moving kids along. Also, you can change this based on what's going on with your kids. Come on.
Not switching for me.
Yeah, there we go. First of all, one of our big things when we give teachers kits is just simple wooden cubes. What they are is blank die, right? So we give them cubes and we say, take a Sharpie or take stickers and make your own die. You decide. It's empowering teachers. It's not disempowering teachers by saying, follow this very much scripted curriculum. It's saying, it's up to you to understand your kids' development and to change these activities to make them more appropriate for your kids where they are. And that's really a scientific approach that we take, but it's a scientific approach we're asking professionals to take in the workforce. So they can change the cube for that little boy in the very beginning, clearly if he rolled a 4, he'd be in trouble. All right, so changing that die to maybe just be 1, 2, 1, 2, and then a 3 on there for stretching him might have been a good idea, where she may have needed a cube with way more higher numbers. It can be dots. It could be numerals for kids who are already reading numerals. It could be two dice then. It could be 1 with dots, 1 with numerals. There's all these ways that teachers can change the activity, as well as even for the youngest kids who really can't set out that number, we draw the circles on the plate so that they can always add the chips. So we had this little girl in our study who really could not produce 3 objects. There were 2 grad students in there following cases. She was one of our case studies. And they were reporting back, and we're having research meetings all the time, and really could just not move her along. She seemed to be very much stuck. And the one time, we always had to draw the circles for her whenever we were doing any kind of activity that was producing. So if you said, okay, you rolled a 3, she would wait for an adult would draw the 3 circles, and then she would simply match them. And the one time the adult was busy, I think tying a shoe or something like that, something vitally important that somebody was tapping them on. If you work in early child, this is just becomes a constant. And I feel it's payback from burping kids. So someone's tapping there, she turns around, she's helping, and Tanisha's tapping the other side, and she's like, okay, just hold on, Tanisha. So Tanisha just takes the pen and draws her own 3 circles. Like, how long have you been able to do that? God, would have saved us a lot of time in our research meeting. But anyway, we can modify these activities. And this last movie, and then I'm going to sit down for a little while. This last movie is sort of to look at. We use counting as an example. We have so many things in math. Doug's going to talk about one of our geometry areas. This is another geometry area, but it's a nice thing is look at how number comes to play too. This is a teacher-made video.
Rectangle show and tell. You don't want to go first? Bella, what did you bring for rectangle show and tell? Can you show it to everybody?
What's it about, Bella?
Okay, let's check if Bella really brought a rectangle. Let's see. So how can we tell if this is really a rectangle?
Has right angles.
How many right angles does it need to have?
1, 2, 3, 4.
So can you guys show me your right angle checkers?
Well, it has 2 points and it has 2 curves.
Okay, good observation. So show me your right angle checkers. Good job. So let's look at Bella's book. So right here on Bella's book,
Don't touch it.
It has 2 lines that come to a point, and right here it has 2 lines that come to a point. But what about these 2 corners?
Point.
Do they come to a point, or is that a curve? Curve. So it's almost a rectangle. It's really close.
It doesn't come to too.
It's really close. Ava, what did you bring for show and tell?
A scary monster book.
A scary monster book. Is it shaped like a rectangle?
Yes.
How can you tell?
Because it has 1, 2, 3, 4. It has 4 sides and it has points.
And it has points? How many points does it have?
4.
4. So a rectangle always has what? 4
sides.
4 sides and 4?
Back is a big monkey breaking those airplanes.
I see that. Does it have 4 right angles though? Can we look at it?
Let's count all together.
Let's count the right angles. 1,
count all together.
2, 3, 4. And are they straight or are they curved?
They're straight.
Straight. So is that an official rectangle? Thumbs up if you think Ava has an official rectangle. Good job. Is this your favorite book, Ava?
It's really scary though. And on the front is red eye. That's the big bad wolf.
Okay, good job.
Makes people dead.
What makes people dead?
So much math happening right now. Yeah.
But I hope you could hear that girl who right from the get-go said it has two, pointy angles and two curves. She saw those subtle differences. Kids love catching. One of Julie's favorite activities is having little kids catch mistakes in children's shape books. They call this a diamond. Is it a diamond? No, it's not even a rhombus. It's it's got mistakes. Kids love finding that. Oh, you know better math than the people that wrote this book. And it makes them very happy to be experts at that. So, and again, the 2 and the 2, the 4 sides and the 4 corners all form different, now geometric images of those numbers for kids, which is really important to their numerical knowledge as well. But just to prove to you, because this is a little hard to see a learning trajectory, it's a point in their development where they understand parts of shapes and how to be pretty exacting about that, right? But to show you a progression, let's take a look at a different geometric skill, the skill of putting shapes together to make other shapes, like the boys were doing at the very beginning story when Corey and his friends were putting 3 triangles together to make a square, right? So let's take a look at a progression of composing geometric shapes. We don't need the sound on these videos. I'm going to talk over them, so if you want to turn down the sound all the way down, it doesn't matter because their actions are what's important here. Here's a little girl. She's at the pre-composer level. You almost want to say, like Julie was saying before, no, she just doesn't know much, right? She can't even match the right shape to the right outline. But we always look for the strengths. She knows she's finishing a puzzle. She knows she sees some symmetry there intuitively, and if she puts one shape up, the wrong shape, but one shape up for one foot, she's going to put the same shape up for the other foot. So these are important recognitions of an early level. Other than that, she's not really composing shapes or even matching them. Let's skip up 2 levels. Now, I'm going to try to talk about this a little bit. Do you see the lower right? She's going to try right now in the video to put that orange square in where you and I can see only a blue rhombus or 2 green triangles are going to fit. Square's not going to fit. But at this level, she matches in her head side lengths. She doesn't see angles like you and I do, right? So take a look at what she does. She tries to get that square to fit, but then she pushes the square into place, and it pushes the other 2 shapes in the arm out of place. So then she fixes those, holds them down, tries to force the square in there, but it doesn't work. So she gives up on that, and hey, lucky for her, blue rhombus is right next to her hand, and that works. And she finishes the puzzle eventually. But early childhood people like yourselves tend to be very good process-oriented people, and if you watch the process she used, it's head and shoulders above the first girl, but it's still trial and error. So where do we want the kids to get by the end of preschool? Take a look at this little 4-year-old girl. What a difference now, once she's got experience, right? So she sees that robot puzzle. I hope you can see the outline's coming up pretty well on there. She sees the symmetry in that explicitly. Puts one shape on one side, puts a mirror image on the other side, puts one shape on one side, mirror image on the other side. Okay, but 2 other things are even more important. Look at the time she spends looking at the puzzle and looking at the shapes. Unlike the first 2 girls that just grabbed a shape and tried it, every shape she picked fits, right? And the most remarkable thing of all is look where she turns the shape and look where she looks. She doesn't put the shape on the puzzle and then turn it or flip it into position. No. She looks at the puzzle, and on its way over, she manipulates the shape with her hand. She can maintain shapes, build shapes in her head, maintain that shape in her head, and manipulate that shape in her head. And that image in her head directs her hand to do the perfect placement when she puts the shape down. That's an incredible competence on the part of a 4-year-old. And you think not only geometry, think of the visual arts, think of architecture, think of arrays and models and fractions that she'll confront later on in the elementary school. This is a powerful tool leading to all those.
That was amazing. I mean, like if you did play-by-play for sports, if you like sports, you'd be really good.
Yeah, and not so good at
just
not so good at the sports.
That was pretty amazing, yeah.
Instruction. Remember, Julie told you, we have to match the instruction to the kid's level. Most of the time, when Julie and I work with teachers naively ourselves at the beginning, they would just throw out all the puzzles and say, pick the one you like. It really didn't help the kids very much. But these kind of hands-on activities, and we spend most of our time, like Julie said, in hands-on kind of things, but we do computer stuff too, so let me show you. Here's some hands-on activity. The first girl might get one like this. Do you see how separate the shapes are? They're still building something, but they're not really composing shapes to make shapes. We want to help her match. Then we would move that first girl into here, where now, still so easy, all you have to do is match it to the exact same shape, but you start to see how they're eventually going to go together to make a grate or something, matching the sides like that. The second girl would get something like this. Once you put that nose in, if you see it like I do, then the hexagon is obvious, and it's pretty easy, but you still have to think a little bit, right? And the third girl, we got to challenge her, so she gets something like this, large ambiguous areas where she really has to plan out how to put shapes together to make other shapes. And then let's just do the same thing. First girl after she can match the shapes, second girl, and the third girl, where you really got to look at angles. And then that third girl will go to this, and you might say, wait, that's easier. Yes and no. The yes part, it's easier. The no part, once she finishes, the computer says to her, good job. Takes off the shapes and says, now solve it again, and you can't use any of the same shapes. Oh, now I got to substitute some shapes for other shapes in my solution. So that's where we're trying to lead her. And we always let the kids play. Julie invented this kind of free explore, and I love it. What kids do in this free explore level, and that's not, I shouldn't even say level, the free explore activity, because there's no levels on this. Every time a kid at any level finishes their test, they're invited to play with the stuff, right? Whether physical or computer-based, we always have them play. How do you play on this? You pull the shapes out, and then you press the play button in the middle bottom, and when you do, your puzzle turns black, and it's a puzzle you can save or have your friend try. So you make puzzles for other kids doing that. And then there's another one where it's even more open-ended, where you pick a background scene and then you can compose shapes any which way you want, color them different ways, and everything else called create a scene, where we really want the kids to play with it. Here's a 3-year-old who did that. It's a pretty primitive kind of design, but what I love is on the right-hand side, she gave one kid a balloon. Isn't that? It's just cute as heck to me. So, returning to surprise number 5, we know a lot about how to scale up teaching and learning with learning trajectories, right? So our curriculum framework, remember we stopped with learning trajectories? Where do we go from there? Well, we work with small groups of kids once we have a learning trajectory. Is the learning trajectory right? Did the activity seem to help them go to the next level? Then we work in a single classroom, and we bomb that teacher with observations. We got GRAs in there. We visit her. We're there helping her. So it's what Krombach calls a super realization. In other words, we try to make the environment easy and perfect for that teacher to see what the potential is. And then, after we've modified the activities, every step of the way you're refining your stuff, throwing out lessons that don't work, refining lessons as you learn, you go to multiple classrooms. But you're still trying to say, is there enough support for teachers? You are not doing randomized clinical trials for the first 8 phases. You're working with kids. You're doing qualitative research, clinical interviews, teaching experiments, this kind of thing. Only at step 9 and 10 do you do the summative research. So, Julie, I think you're going to talk about the scale up when we go to summative research and then head towards district-wide.
Sure, we only about 15 minutes, so we're going to go a little shorter. So the scale up then. So we took Triad, the building blocks curriculum, situated it in what do we need to do, and came up with Triad, which is I've heard about it several places. Acronyms, as you know, are key to getting funding. Carolyn Ebanks, our program officer, isn't here, but I'm pretty sure she chose us because she was like, oh, Triad, like that one. But anyway, Triad stands for technology-based, technology-enhanced, research-based instruction, assessment, and professional development. but it's in there. Professional development is all in there. So you have to fudge to make the things work. It's like STEM, Daryl. I mean, we could say science and math are the anchors, or we could say that was the only way to organize those 4 letters into a nice word. And I kind of feel it's the latter. But I like it. Yeah.
Nothing else
No,
really
I'm going
works.
with it's the anchors. I think that's a better story. All right. Go forward. So we had research guidelines. Really, again, if we're going to take this to scale, we have to start just like we did in Learning at Kids Learning. What did anyone who ever took anything to scale find out works? So we came up with some research guidelines. We're not going to go through all of those, but the idea was to really take all these into effect. And if anyone's going to do scale-up work, this is the kind of groundwork that has to be done. So we did not go to scale for at least 3 years of really getting our act together. Keep going. And number 6, I'll be talking about later, where we talked about the professional development piece and what that looks. I'm giving a talk on the professional development piece specifically. And so we had these 10 guidelines. We had 11, but again, that doesn't really play well. So we cut one. And what we did is we did it with groups of teachers, and this actually was in some public preschools, some Head Starts, and some CBOs that had Head Start classrooms. But really, in the places we worked, to be fair, they were very much maintained that CBO, the child care center type environment. What we did is some of the teachers did business as usual. Some teachers came and did professional development at the exact same time as other teachers doing professional development. What was the difference? One group got professional development on learning trajectories using building blocks, but really understanding learning trajectories, and the other one had activities. And so when we're looking at math activities right now, we're looking at math resources, really what you get is, this is a good idea to do so. You know what you could have kids do? You could have them count the chairs. You know what you could have them do? You could have them find the rectangles. You know what you could do? You could fill up that water and spill it out and look at volume capacity. Yes. But the difference is it's not carefully sequenced, and it's not based on what kids are doing. So to have every kid count all these chairs in September and then again in May makes no sense. We wouldn't think that that's right for anything. We wouldn't say, what's good to do? Read One Fish, Two Fish, Red. We wouldn't have them read that book every day for a year or a day. You want to pick the right book at the right time. Likewise, you want to pick the right math at the right time. So that middle bar was some math. Good math, it was a full year curriculum, but it wasn't sequenced, and we specifically didn't teach teachers how to modify activities based on their understanding of kids' development, no learning trajectories. And we had evidence to move forward and say this approach might work. So we did it in a large scale up with lots and lots and lots. How many classrooms?
167.
167 classrooms in 2 cities, actually 3 cities, but this only counts for 2 of the cities because the other city was just so different. We really couldn't work on it. It was more of an ad hoc. And again, we had an effect size of 0.72, which is a fairly large effect size when you take something to scale like this. Go ahead. And
so we're going to return to that study, but first a few more surprises based on this kind of we know research and the like. One of the surprises we wanted to bring up, and incidentally there is a handout that we wrote for the Educational Commission of the States, or ECS, that covers all these surprises. So we're happy to share that in a written form. It's nice, has all the resources, more text and pictures than just the slides. One of the surprises that we think is real important is math and play, because sometimes when we go to policy people or administrators, they say, well, actually, we believe in play. So do Julie and I. And we tell them that. And we say, there's really no contradiction there. Well, I don't know. We don't do science and math. We teach children. We don't teach science and math. These kind of bromides just don't work, because if you look at the actual research, math and play, highly related. Building mathematics knowledge doesn't mean sacrificing play, it means enhancing it. For instance, Herb Ginsberg research. What he did is he looked at low resource classrooms and higher resource classrooms in New York City, and he had his grad assistants videotape free play, just unguided free play, and wanted to look at the average number of minutes, they coded every minute separately, that they saw something mathematical in kids' free play. And they first thought maybe 5%, maybe 10%. We don't know how much math they do spontaneously. No, 42% of the minutes had math in them. Now, we disagree with her just a little bit on his next statement. He says it's math. We say it's math foundations. We don't say it's mathematics. We think it's an intuitive foundation because, and part of the reason for that is because we think if you don't have the language of mathematics, you won't be able to connect that kind of play to when you get to school mathematics, right? What backs us up on that is the optimistic thing Herb found is almost but almost no significant difference between the low resource kids, these were very poor children, and this really highfalutin preschool where you had to sign your kid up at birth and it was $20,000 a year to, you know, and above, no difference. 42% in both settings. But those kids are very different when they go to kindergarten, and the reason is they don't have the benefit of somebody talking to them about the mathematics that they do every day, giving it the mathematical language and the like.
And understanding where they are, right? We don't, even if we go back to that first story about the math potential and little Corey with the squares, it was the teacher saying not only good job, not the, you know, which would be, oh look, they're doing a puzzle, that's cool. How many triangles? Great, she did something. But then finally, how many squares? Right? That involved her understanding math and kids' mathematical development. That's the key.
And you're up next anyway, Joe.
All right, and the next study was that math and literacy, language and literacy do not suffer. So when a big thing happened in the scale up is we were working in districts that, large urban districts. There's lots of initiatives. You know, it's the reality when anyone comes into, we were in another panel yesterday with successful longitudinal things, and they all had in common is that they could be successfully added on to what teachers were already doing. Because teachers are inundated, especially in large urban districts, with different things happening. And so here in our districts, literacy had been the focus, the primary, some would say the sole focus for a very long time. And when we came in and we started doing math, the teachers were very worried that literacy would suffer. You know, this is going to be a problem. So we were pretty sure it went in, and I tried a bunch of things. One of the things I did is we said, okay, let's do this small group activity together. And we, you know, because we do the small group activities with the teachers, and we would time it, set a stopwatch and time it. How long did that take? How long would this take to do your whole class? Is this really going to take time away? Let's do the whole group. Let's time it. Let's substitute out calendar and do this math and whole group instead. And, you know, really tried to like scientifically convince them that that really didn't work. It's more of a sense, right? I'm worried about literacy. I'm just worried about literacy. So what we decided to do is post hoc, after the kids had entered kindergarten, we went and assessed them on a language measure called the Renfrew Best Story Test. You tell a story of a naughty bus. The grad students have it memorized. I think they have nightmares still about it. There was a naughty bus, da 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 da. They tell this whole story in only pictures, and then they ask the children to retell the story. And we also gave PALS, letter naming. And when we gave those two assessments, so this is a delayed post-assessment, what we found is there was no difference on letter naming or 3 of the expressive language measures. And really, that for us was a success. So we did no harm. The kids, even though the teachers were focusing on math, the kids were fine. But this is the cool part. The kids in the triad group did significantly higher on information, grammatical complexity, independence, so they didn't need as many prompts to keep going when they're telling the story, and being able to answer inferential questions. Why do you think the naughty bus did that? So this was a really good result for us because it's kind of tied to what Doug was saying about the language. Now, some people have reduced it to say, oh, well, then it's really just about the language. No, there's significant math going on in the math instruction, but the language is a key component. One of the Vanderbilt GRAs, I think, called it a talkie curriculum or something like that. It involves the teachers. The teachers are always saying, how do you know? Why do you think that? And asking kids to explain their thinking. So over the course of the year, the kids get very comfortable answering these sort of longer questions, and we did higher. And that led us to go into our next big project, which is really where we started to talk about, could we indeed take that sort of great result and build off it? And so what we did is we got together with Nell Duke at University of Michigan, Kim Brenneman, who was at Rutgers at NEAR, now she's at Heising Simons Foundation, Mary Louise Hemmeter at Vanderbilt, and we said, all right, the 4 of us get together, and the math definitely incorporates language, and the literacy piece has math books and science books, so it's bolstering both. And the science doesn't ignore the fact that math is happening in still a trajectory way, so we're not counting seeds up to 5 in May, because that's when we plant our garden, but instead maybe we're doing really hard measurement, because that's where kids are on a learning trajectory.
And shape composition.
And shape composition. And at every point in every small group, we are asking ML's team, how can we make this better from a classroom management perspective and from a socio-emotional perspective, as having also very targeted lessons towards socio-emotional learning. So that we took another direction. That's still not an efficacy stage, but we are building after that on that nice result and taking it in another direction.
So stay here, because I think you're up in a second.
I'm
anyway.
happy standing here. Thank you.
Here's a totally different study. I'll try to go real quickly with this, but it's a pretty complex study, as any of these kind of cluster randomized designs are, but it just tells us one other message. So I'll give you the message first and then a little bit about the study. The message is, we were surprised in this one. We were mostly disappointed in how the results came out, except for one, and that is, math seemed to raise executive function, even though that wasn't our initial hypothesis. Okay, what did we do? We took our building block curriculum. We had Elena Bedrova and Debbie Leong from the tools curriculum synthesize it into tools, so that we had this combined tools plus building blocks. And then we hypothesized that we would get better math in that than just building blocks alone, and then better math in both building blocks and the synthesized curriculum than a business as usual. So there were those three treatment groups.
So the idea, right, I've heard it in a few sessions now, where people say, if we focus on self-regulation, the academics will follow, because kids will be able to better learn if there's better self-regulation. So that's what the hypothesis we were going in there. So if they were doing tools, and building self-reg at the same time they were learning the math, those kids ostensibly would know more math. That was the hypothesis.
It didn't work out. The tools plus building blocks curriculum, for a variety of possible reasons, we're still doing analysis on it, but it probably is that it just was a little overwhelming for teachers, right?
They couldn't do both.
They couldn't do both. And there was also some conflict between us and Debbie Elena. Like, for instance, their tools ideas, you cannot take kids out of play, ever. So we said, well, they only have one computer. We'll never get them through the computer activities. Can we just take a kid out for 5 minutes? No. So we disagreed with them on that, but we went with them because they were the tools.
They're bigger, really.
They're bigger. Scarier, maybe. What happened? They learned less math in the building blocks plus tools than the math group. But the interesting thing was, and you see it there, it wasn't ubiquitous, it wasn't large, but the building blocks alone group was the only group that gained in self-regulation skills. And we weren't even teaching those skills. So this idea that we gotta make sure they have self-regulation, and here I might be disagreeing, and we'll have to see with Stephanie Jones this afternoon, is that well done science and math and engineering activities may be one real great route to developing executive function. For our original idea that a lot of people had, not ours, but the field, build self-regulation first so that they can learn academics, may be a little too unidirectional here. But it's just one study. It's just a trial.
But there were other studies that kind of linked to the same thing.
Yes.
That perhaps doing really engaging activities builds self-regulation, and so really it's bi-directional. We're not saying, no, then you do this or the other. It's not a complete disagreement. It's saying we really have to look at both. And again, in working in the C4L classroom, where we're doing much more of everything.
On purpose.
On purpose. You really do see, there are places where teachers cannot get started because you have kids going around, there's those 3 or 4 kids who just want to whack everybody on the head. And so if you're constantly putting out fires, you can't get anywhere, right? We need to establish protocols and schedules and visuals and problem solving and all that. But at the same time, and once you get the kids highly engaged, those behaviors go way down.
And they love science activities, and they love math activities and engineering activities and technology activities. So STEM, again, becomes one route for classroom management. So all these things, as we know, are of an ilk. But when we get our researcher hats on, we often postulate, here's my theory of change, and it's, I developed the self-regulation, and then we do this, and then we do this. Not so. Little bit. We got time, Julie? Little bit of the classroom?
So just
Sound back up, please.
Jamaica Plain teacher Meg Johnson is not looking for the answer square or rectangle.
Now this is a rhombus and this is a rhombus. Do they all have 4 sides?
More than dress up and nap time for the 3- and 4-year-olds, these preschoolers are learning geometry and counting. No memorization, no math tables.
I see fingers popping up. I see how many.
To be quite honest, I was skeptical.
This mom wasn't sure if her 4-year-old son Camden would get the subject. He did.
Oh, Mum, 10 plus 1, that's 11, isn't it?
How many now? They want to count. They're counting going up and down steps. Do they have enough snack?
Even playing dress up involves math. Here, they're paying for things and counting the money. Each station can have 4 children. They know when they hit the limit because, well, they can count the number of dots.
This is 6. What's this?
9.
That was quick. How'd you do that?
Because I just counted 9 in my head.
Just 7% of 4th graders in the U.S. are at an advanced level in math, compared to 38% in Singapore. And according to research, kids exposed to math early struggle with it less later.
They think math is fun. They know math. They know they can do it.
This is the number 1.
It definitely will give them that solid foundation to push them further. 10, 20, 30, 50, 60.
You forgot 40.
When we learned, it was all memorization, at least when I learned math, and I was never comfortable with math. I can look at my curriculum and say, this is where this kid is. These are some activities I can do to really push him.
All adding up to a brighter future. I'm Bianca De La Garza, News Center 5.
I'll confess here, my 4th grader asked me what a rhombus was yesterday, and I had to Google it. Honest to God, true.
I'm so proud of you, Bianca.
Half funny, half sad, right?
Yeah.
Can you imagine her saying, I can't really read my teleprompter, so they have to tell me what to say in my earpiece? She would never. Math, it's okay. It's a cultural thing we have to change. So a couple other things about that. You might not have noticed, or I don't think you could have noticed, right? One thing you might not have noticed is it flew by, but she said a really good thing about learning trajectories, right?
So she says one thing I can do is say, this is where my kids are. These are some things I can help them to get there. That's the learning trajectories in a nutshell, right? Where are my kids along this path, and what are some activities to get there? She really internalized the idea of learning trajectories. And that doesn't come right away. That's over a process that takes time, but Meg definitely got there.
Oh, geez, if we can build one more thing on how Meg does that, Julie. When she says to the little boy, this is 6, this is 9, how did you know that was 9? I just counted. And then it goes,
I counted 9 in my head.
I counted in my head. And people laughed a little bit in here and stuff, and it goes on to the next scene, and I asked Meg, so that was a good enough explanation? She said, no. When he said, I counted, I said, how did you count? And he said, well, I knew this was 6, so I then went 7, 8, 9. I knew that had to be 9. Good job. But they didn't think that was cute in the editing room, so they cut that part out. But that's what Julie's talking about when she says, how do you know? When you have to dig deep like that to explain and think about your own thinking, it really is a metalinguistic kind of thing that probably accounts for our language bump.
Well, and even when you go back to that classroom, that little chaotic classroom with bringing the rectangle show and pal with the books, and she was saying, what did you bring, a rectangle? Really, it's a big leap for our teachers to stop saying, great, next. Or, to really say, how do you know? And it takes a lot longer. And we really didn't want that whole group to go on as long as it did. Trying to get people to shorten their whole groups is a difficult thing. But the fact that it was always a conversation, she knows those kids are expected to defend their ideas about why. And the kids start adapting it. They don't start off saying, oh, this is a rectangle because it has 4 straight sides, and let's look at those corners. But she starts offering it. Is this a rectangle? What about the corners? Are they straight corners? Let's look at those. And she hears points. Okay, go with that. There are points. These are 2 points. What about here? Are these curves or straight? Oh, okay, there's, that kind of thing. It's a conversation about math, and the kids start doing it, and you can tell because when the one girl says, let's count together, really mimicking, right, what the teacher said. Those conversations, they don't start off in the fall happening automatically, but they do happen.
The child also, if you noticed, was very careful on the rectangle here, counting the sides by going like this, 2, 3, 4, and the corners, boop, boop. So another instance that it's really the teacher helped them with this kind of visual aid, separate what sides and corners are. A lot of kids will say rectangles have four corners. You ask them, they point to the sides.
She was still a little confused on that in the video, but whatever. Okay.
Long term. What do we find long term in this? Long term is sustainability, persistence, or diffusion, right? Sustainability is, do the teachers maintain the fidelity to this, or once we pull out the coaches, we leave, we say, thank you so much for participating, we give them a little gift, we're gone. They say, okay, I might do a little of this next year, but I did it for you guys this year, and I'm going to try some other things too, and that was a lot of math. I'm not sure I can keep that up all the time. So we were worried about that, so we went back. We first went in the fall of the year we collected the data, and we found pretty good fidelity. Those bars are not supposed to be the same height. We had more fidelity Likert scales for the small group than we did for general curriculum. So it shows a pretty good. They averaged well on this one. Then we went back in the spring, and good, they got a little better. Wasn't huge, but a little better. That's great. Then with a little bit of fear, right? Our stomach's nervous. We went back 2 years after the end of the project. Were they still doing it at all? Is this going to fall off like the research says? No. Went up a lot. Then we looked at all the factors that accounted for that. In other words, some teachers still went up more than others, right? The biggest factor that accounted for that is child gain, measured child gain by us, which we never told them how much your kids gained. So we assume, and I think it's a pretty direct causal line, that they saw the gain on the part of their kids. And the ones that saw the most gain said, I am doing this for all my children, right? Follow through. You want to talk about follow through? Keep going. Okay. Follow through. We didn't have a very good follow through. We could kick ourselves around the block, but we were exhausted and the funds were, not huge. So we actually had 3 groups. Julie kind of talked about 2, and that's right, because we were talking about preschool. But we actually had 3 groups. We had a business as usual, a triad group in preschool only, and another group of teachers who were triad in preschool, but also we work with the kindergarten and first grade teachers. And so what you see here is, of course, here, at this point in time here, sorry, Daryl, at this point in time, the difference here is the same. These 2 groups are the same because they were in the same treatment. Okay, that just makes sense, right? But then they separated and only the red line got the follow-through. It wasn't a very powerful follow-through. That's why we're a little disappointed. We kind of told them about the learning trajectories, how to use formative assessment.
I mean, we had, and some of the teachers had maybe 1 kid who had been in the preschool condition, and some people had 10 kids in their preschool condition. So it's a little more difficult to convince the person with 1 kid in that condition that it's worth their while to come to PD and learn about learning trajectories. Horrible quote by one of the kindergarten teachers that I was emphatically pleading with to come to professional development. She said, I ain't got no stars. So, it's just with that attitude that you're happy sending your kid to kindergarten. But, so we had to start all over again getting buy-in with kindergarten teachers. We didn't have a year of gentle startup where we could just work with them to learn things. And they had a pacing guide given to them by the district, which kind of, hamstrung them a little bit about how much they could do. So those were the limitations of the follow-through condition.
But it still maintained more of the gain, more of the distance between the control group and that. But we tend to throw these gains away, right? So the message to Julie and me is we need to do better than this. If we had done the same thing we did with the preschool teachers, the same intensity and duration of professional development, there's no reason these kids can't keep learning like this through the primary grades, right? We also followed these kids into 5th grade, and You see the same thing, the kind of catch-up of the other kids, and then a bump at 5th grade. That's really funny that we think comes from 5th grade being a really challenging year in standards across the country, including Common Core and everything else. All of a sudden, proportionality, division, ratio, operations on fractions come in. That's when all of a sudden this early cognitive foundation on the part of kids, composing shapes and all that kind of stuff comes to play. And so the effect size actually reemerges, a kind of resurgence of that. Diffusion, Joel.
Really quickly, so there was diffusion. It was something we said we would talk about, so we're going to give you like the 10-second. This is being used not only in Boston, but in the surrounding area around Boston with different suburbs, Chelsea, things like the people picking it up and doing it. They're also making pre-K count, New York City initiative, so it's being done in New York City schools and still continues to be used in Buffalo. The idea is that we stepped away a long time ago. We did take the time to follow those research-based guidelines to adapt to local policies, adapt to local control. So when people come to me, putting in a proposal and said, so do you, how often is PD? How large is PD? How many is this? I say, well, what's the environment? My first question is, let me find out from you. Can you use local coaches? That depends. Do they have the capacity? That kinds of thing. So in the places where we really did let it go, we stepped away, and it not only continues, but it spreads. So I think the lesson isn't that, oh, we did a great job. The lesson is that we just listened to what other people did when they said, this is how to do a great job. And most people say, let's start over, what should we do? And when Daryl says, well, we've done the work and we can use us as a model, it's only because we've used others. And we didn't maybe have another early childhood area to look at, but we looked at diffusion research across the board. How did during the AIDS epidemic, how did they get to change health practices? How important was it to find target influencers and things like that? So doing your work really matters.
So real quickly, this ends the surprise portion, and then Julie's going to talk about specific research lessons learned. So, but just to review this, we talked about early math having surprising predictive power, that young children have the potential to learn powerful mathematics, but that's a surprise to too many educators. We talked about that most children need an intervention, and finally we spent the longest time on, we know a lot, learning trajectories, interventions, how to do it. So what lessons have we learned? What implications are there for practice and policy?
Really quickly, and I'm not going to do every single bullet because that'll drive everyone a little crazy, but educating the workforce was the key thing. There are no silver bullets. It is in the details. Still, people will come up and say, we heard you had success in Boston with building blocks. We'd like it. As in, you're going to buy the books from McGraw-Hill, and you're going to give it to your teachers, and done. And if we say, what do we need to do in order to do that, the key is educating the workforce. And dare I say, treating them as professionals who can be educated. Even if you commit to professional development, when we come in and it's like, oh, we can't ask them to bring their books because they won't. It is an us versus them kind of approach, and it doesn't bring in, and we treated teachers as professionals, and so we have to say, look, it's not just the curriculum. It's instruction, yes, but it's assessment and professional development. We know that it's more effective if it's based on scientifically validated early childhood interventions. We have to go way beyond cute ideas. That's a good idea. We could have kids do this. We have to be very systematic and scientific and not idiosyncratic. Again, we're looking at resources for early childhood, and still too much of it is, things you could do with your kids. Yes, you can sort shapes, but if you're sorting the same shapes year round, they're not moving them along a trajectory. We've found that does far from hampering teachers. It allows them to be creative because it gives them the tools and the understanding that allows them to riff off of that in a good way. We talk about productive adaptations, not lethal mutations. If you're doing a game with dice, don't substitute trouble, because then the dice doesn't fall on the ground. That's a lethal mutation. It doesn't allow you to differentiate. It changes your goals completely. We talk about how to make the game yours, and teachers love being able to be creative with the ideas, but to still be scientific. From a research review, it came across, this is not just us, consistent 50 to 70 hours of professional development is important, to be situated in the school, to have mutual respect with professional development and coaching. And learning trajectories were an important thing. They were a way to talk about kids. So when we come in to coach, we say, how is Doug doing? What is he? You know what? I thought he was a producer. I really did. But now I'm looking at him and he's counting objects in all different arrangements. I think he's moving up a level. Those kind of conversations are easier to have when they're around children, and they get right to the content piece, so it seems to be important. We don't like to fudge on that, and yet still we get asked to fudge on that, the biggest thing. Oh, could you do a little bit less professional development? What if you did a really big institute in the summer? Do you still need to inoculate them halfway through the year? Yes. This is hard. This is very, very, very hard stuff. It takes a while to understand it, and really what we say is people don't like to do it, and then all of a sudden when you come back in the spring and their kids are learning and they get that feedback, then it's positive. But we meet with teachers once a month. We try to do interdisciplinary, but it's not all integrated. For the people that say, look, I do math sort of all day. I do math every day. I do math all day. My question still is, what math are you doing? And for what purpose? You know, going back to, again, planting seeds, everybody's been in classrooms, right? I'm integrating math into science. We're doing a garden. And what's the math? What are my math goals? They're counting the seeds. How many seeds are they counting? Less than 10. Is that your math goal for May? Because let me compare that to your math goal in the fall. If it didn't change, I'm not really thinking that you're doing a large job in terms of moving kids along. So instead of trying to continually integrate it, to really think about, okay, we're doing math, but we're trying to meet kids where they are. One of the big things is consistent communication. We really thought that it was communication between project and teachers, and really what we ended up doing is facilitating communications between different components, staff and teachers. So the mid-level staff, the early childhood coordinators, inviting them to professional development, meeting with administrators constantly and trying to get them on board, and really understanding what their children and their schools are learning was really important. And what happened was most important was the mid-level staff. So those had the most contact hours with the teachers. So the early childhood coordinators, they come to professional development, and for example, we'd given the teachers really bad feely boxes. We needed feely boxes. They're not part of the kit that McGraw-Hill provides. So pretty much it was grad students with a hot glue gun and socks. And I'm not sure about our OSHA violations on that one, but there were maybe a few burns. But anyway, they weren't pretty. They fell apart. They weren't good. We tried Velcro. We tried a million different things. So the early childhood coordinators were there when we handed these out to the teachers, and they said, you know what? We have some of those in storage. We're going to make sure, so they stood up and they said, everyone will get a feely box that they were going to provide. That was more than, oh, they got a cool new feely box. That was saying that the district, the people who are going to come in my classroom and see me, believe in this and believe is the right thing to do, so it's a real implicit message. And it was nice to keep that communication going. And of course, we needed to build flexibility with Head Starts having sometimes 4-day-week, half-day schedules, et cetera, and giving teachers the tools to be able to work in. Again, understanding that math is hard. Teachers come in saying, you heard Meg, you know, math was always difficult to me. I was taught it by rote. Teachers come in with biases of Bianca Del Grasso saying, I didn't know what a rhombus is, right? They come in saying, I don't know the math. And now we're asking them to know the math and to understand how kids learn. It's a heavy lift. The first few days of PD people feel like they got hit by a truck. They're like, oh, I don't know if I'm this is a lot. This is a lot. How did you like it? It's a lot. You got the days, and they'll come through, and the leaders that we work with will say, is there a way to make it a little easier? And my answer is just no. Really, no. This is hard. This is hard, but if you really hate me when you see me in November, December, and like, oh my gosh, we're doing this again, all of a sudden in January, February, it clicks. It clicks, the kids are learning, and then they're like, oh, this makes so much sense. And when we work with teachers, we say, look, I know these level names are hard. You can come up with your own level names if you want. I don't care about the vocabulary. What would you call it? And we go through like, well, actually, that's not a bad name for it, but it has to make sense. It feels overwhelming. It's not easy, but you would never walk into physics lecture, freshman year beginning and go, this is, is there a way to make this palatable or easier, lighter? No, it's going to take you're going to take a while. It's going to take a year, but then this first lecture is going to seem easy for you, and it does. Teachers get it. But if we keep thinking that it has to be super easy, we're not respecting the workforce. Being an early childhood educator is difficult. Nell, our colleague on C4L, always says she would like to see how many high-level decisions are made in a typical 1 hour. You know, let's just take 1 hour. How many high-level decisions are made, and compare it to somebody who's doing surgery. And she doesn't think it's that far off. You know, maybe the stakes aren't as high, maybe they are. But the fact is just keep thinking that we have to go low and do pipe cleaner people and talk about our dreams for early childhood in PD. We're aiming low, we're not moving the field forward. And then you could do the last.
Real quickly, we got to recognize that some teachers have limited technological experience and provide a technological mentor. That was really important. They need feet on the ground kind of help with that, where we use teach a person to fish rather than give the person a fish kind of approach to help them do that. And so that's the end. I want to end where we started with that we really think this is a good way to start what we need, which is better math in our society. So to convince you that one last time, here's my favorite sign that you see outside of a town. You see some cool math facts. So the population is 562. Great. How many feet above sea level? 2,150? Okay, that's interesting. When was it established? 1951? Great. But what you all really wanted to know, the total of those is 4,663. So we definitely need better math, and we think starting early is the best way to get there. So thank you very much for coming. We're open for questions. Daryl, are you going to lead us in questions? Okay. Who's got a question? Mike's right there. I hope it's on.
Okay, I have a couple of questions and comments. So when you were talking about, the videos you showed, and when you were talking about the concept of numbers, all I saw was what in developmental psych or cognitive psych is referred to as the cardinality principle. I didn't see anything kind of like raising the kid to that other level, which is analog magnitude estimation. And this is really what we want. I mean, what we saw was different step of the cardinality principle. And I was a little bit uncomfortable when you said in the first video, we see that she understands, that she comprehends. Maybe that's because I work on comprehension including of numbers, and when we mean comprehend, we need to really agree on what we mean in terms of the concept. So I think that I would like to see that it's taking the kid to that other more abstract level, and I didn't see that.
So the counting trajectory goes really far, right?
We only showed 6 at most levels of about 24.
Okay.
And we started off with the lowest, right? And we started with those. Yeah, we started with those very low levels because they're easy for most people to get a handle on who don't study early math. For someone like you, when you saw with that boy in that thing doing what number comes next, immediately I could say he's looking at a counter from n, which is at a much higher level, right? So he's able to start at 6 and go to 9. That would be a higher level without objects. But we were really focusing on what is a trajectory and not the entire trajectory.
Okay, and then I just have 2 suggestions with the link with language and literacy. So there is some interesting work by Tare and Schatz on how parents talk to children about abstract concepts like number. And it's very clear that with these concepts, they tend to embed the words into long, relatively long sentences because, because it's the abstract concepts and the children don't understand them, So maybe one thing to look at is how do the teachers kind of, when they start talking about this, if they naturally do that as well. Because obviously when they're looking at parents, the parents were not taught to do that. And we have replicated the studies across different languages. So it seems that there is something that we do when we talk about this. And the link with literacy, I wonder if, if you take the concept of print and what is letter naming, which is one of the kind of literacy pre-skills, before you go to the abstract concept of the grapheme, you need to pay attention to the geometric features. So here you may have some suggestions.
Very good. We couldn't do everything we could talk about with math and language, but well said. The complexity of that. But remember when Julie said that study that they, even in a narrative story with no mathematical content, They talked in long sentences with greater grammatical complexity. So certainly, this reflects the fact that as they get in these conversations with kids, they're using increasingly lengthy, complex constructions to talk about the math. So but that's very important at home and school, like you pointed out. Excellent. More questions for us. Critiques. Oh, sorry, okay.
Did you say that you had some comparison or something with PALS?
We just used it as a again, to really address the fear from the teachers that we were affecting literacy. You know, we were happy to have a...
Because PALS must be universal. I'm from Wisconsin, and the 4Ks use it there as a...
Yeah.
So, and so what did you...
We just gave it as a quick assessment. We only looked at one piece of it. We looked at simple letter naming.
Actually, we didn't even use it in that original study. We used it in the C4L study, the whole PALS. This one, we just got the district to give us the PALS letter naming information. Right. So that was all. The Buffalo and Boston happened to use the same part of the PALS. So we were just grabbing it because it was available in that study.
Yeah, and again, the idea was just to see, do the kids still know their letters, even though the teachers felt that they had done nothing but math. What we'd really done is opened up their eyes and sensitized them to the math instruction, and that felt overwhelming, but really it wasn't horrible.
Not dissimilar to what you were saying about graphing. When kids study the simple shapes and build shapes with sticks, some of the shapes they're building are alphabet letters. And even if they're not building alphabet letters, if they're building traditional geometric shapes, they're building these kind of images that help them interpret alphabet letters and the like. So, you know, you might take some away, but you give some back when you do geometry time-wise.
Anything else?
Cool, more. Can you use the mic? I think they're streaming this, so people want to hear.
Do you provide your professional development any other way rather than in person? Do you do this online, or how is that?
So that's
your later session.
Yeah, so I'm going to talk about that a little bit later, but pretty much the idea was, you know, when we did this, we did in person because we wanted to model what happens in real classrooms. It was pretty foundational for us to think that that we wanted to also use the learning trajectory approach with teachers, not just about math, but that teachers are also following a trajectory in their own understanding, and that multiple modes of delivery were important. So we did whole group, and we do small group, and we have centers. And really teachers moved and rotated really much like an early childhood classroom, and then had time in the afternoon to discuss and go back, and the second year doing case studies and things like that. So really for a long time we are wedded still slightly to that in-person thing. I would hate to ever give that up completely. However, moving forward, you know, we did use a technology piece that is a website that for teachers to use, especially with coaches, for all the time in between. There's lots of times in between, and we know coaching was such a huge part. So taking that to scale in a way that takes it into rural areas. With our C4L work, we've been working much more in childcare world, which is very difficult for people to get out of the classrooms for full-day PD. So we've been developing, we have money from Heising Simons and Gates Foundation to develop better technology for that purpose. So new up-to-date websites with more videos, better videos, that kinds of things that really works, as well as supports for teachers and more importantly, support for professionals that are working in distant areas. So I don't think you would ever take away that human connection, but I think that there's ways for it to start moving more and more remotely, where we're doing support at a distance. And by we, meaning a group of people that really understand this at a deep level.
And the National Center for DTL, the Development, Teaching, and Learning that we're a part of, we're reviewing resources, and there's a lot of these kind of videos out there. What's different about our website is it follows learning trajectories. So it uses the videos to get you to know more about the math, more about the developmental sequence, and all the way up, and then to second grade, actually, in this particular project, and then how to connect instruction to the various levels. So we're making those connections to people. That's what is, to us, the unique contribution.
Right, but what isn't there still is so in all these projects there was coaching as part of PD.
Yeah.
And if I still think that's probably a very necessary component, at least when you're really learning it the first couple years. And we don't have the system up yet. I'd like to have it where people could, do something like my coaching partner, where they could submit their own things, and we could have discussions remotely around learning trajectories embodied in their classroom, discussion groups and the like. Math is hard. People don't do it on their own. Saying this is a cool website, go play with it, that just doesn't happen.
I have a sort of a two-part thing. My concern is the $64 question really is, how does it really get built in so it's going to last? And to what extent do you work with school systems or administrators as well as teachers? And also, of the teachers that really use it, do you know if they continue a year or two later? In the area of clinical and counseling psychology, there's all kind of research. You can bring in new programs, cognitive intervention, behavioral therapy. They'd use it, it makes a difference. You go back 2 years later, they're not doing it because they went into the field to spend 50 minutes with clients and talk to them. They're more concerned with what they want to do rather than what the outcome is.
Sure. So yes, and yes. We really work with administrators at all levels, all the time. And again, we found that in different districts.
It's part of the triad model.
Part of the triad
communication
model.
part. We had to be fairly brief, but it's an important
It was, yeah,
part
and I
of
think
the
it was
model.
in there just briefly.
Can you go back to slide 70, please? I think it's 70. Go ahead, Julie.
The idea is that identifying, using the literature on diffusion and scale up, you need to identify the key people in that district. And sometimes it's not the top administrator. Sometimes in public school systems, it's the principal, right? Clearly, I have to do what my principal tells me. Sometimes, and again, in the school district we work with, early childhood, pre-K was kind of left alone, and K-12 was the focus of the principal. So the pre-K answered to these mid-level early childhood coordinators. And so those were the people that we needed to get on board and really influence. In San Diego, when we worked, there's early childhood directors, and then there's the center coordinators, and all these different peoples. And so one of the key things is to identify who those people are that you have to convince is a good thing, that they serve as the influencers as well as key teachers. Because sometimes you have a building that has 8 classrooms. One teacher sitting in the back like this means everybody sits in the back like this. And so we lay the groundwork to get people on board, and it is a 2-year commitment of professional development. So this is what Doug presented.
Yeah, you might have missed this, or we just went over it too fast. But this is our teachers, how well they were teaching the curriculum during our intervention in the fall, during our intervention. We did go back 2 years after we pulled out the project, and they were teaching more of it, not less of it. 2 years. And I didn't say this, so thanks for your question, actually, because it's not just repetitious. 4 years after that, 7 years later, is our latest data. I don't even have it in a chart because we just analyzed it and the like. They went up again. Now, the only caveat I want to say, to be totally full disclosure here, is many teachers have retired since then. So you might have those teachers that are just so jacked on this stuff, that they stayed. So take the increase again with a grain of salt. But that's 7 years later. They're doing more of it than they did when we were there. And we think it's because they see the kids thinking, and math is finally interesting to them rather than a chore to kind of grind through.
Right, and I think because again we built on the shoulders of giants. People had done this research ahead of us about how do you sustain. And the problem is when most people do intervention work, they come exactly like you say. They come in, they do their intervention, they get their post-test scores, they go, all right, let's go. I did it. I was a grad student. My dissertation ran into the teachers with whom I worked, 2 years later in the grocery store in line. One of those awkward things that the length of the conversation is determined by the number of items in your cart. And so, you have to keep talking until somebody finishes done. So she says, oh my gosh, my kids learned so much math that year.
That was the best year I ever taught math.
I ever taught math. And I'm like, so you still doing it? No. No. So even though the opposite, even though she saw the gain in her kids, she saw the effort to be too much because I hadn't done the groundwork of giving her support. She was in isolation. It was 2 teachers I looked at in isolation, not as part of a system. I hadn't addressed all the other things.
We tended to teach her activities, not kids thinking.
Right.
We weren't into that ourselves yet.
Yeah, we didn't teach her anything
A new
about
curriculum comes along. Well, that was the best year I ever taught. Now I have this new curriculum. Right. So you know, from our point of view, how can you abandon the stuff you were doing when it was the best year you ever taught? Well, that's how schools go. Comes and goes.
So yeah, when we started this off, we took a lot of time to look at what other people had found success in and exactly addressing those problems because that was our experience. We called it the next big thing problem, right?
More, not much time, but a few more minutes.
Speaking of building on the shoulders of giants, I'm curious about science learning trajectories and where we might start, what we might do.
Daryl, go.
Yeah.
Daryl, finally you get to do something again here.
He's doing his email, I think.
We're really following the lead from Julie and Doug in terms of thinking through this. And as they point out, it's not something you can do in a day. It's a huge amount of work. It requires partnerships with teachers, lots of videos on kids, and lots of time spending trying to understand what is critical and what the trajectories look like in science. But we're working on that, and others are working on it, and we have these giants to follow. So stay tuned.
Daryl, I would love to hear your answer to my supposition, based on the little I've read about science, because I'm no expert like you are, that there are burgeoning learning trajectories within topics in science, but they probably aren't as highly interrelated. In other words, if you do water play before you do block building, it really doesn't probably make as much difference, whereas in math, doing subitizing before counting really helps. Doing this kind of geometry right at this point when the kids are here helps their number knowledge. So they're not tightly linked, but they're a lot more in an entire system than maybe science is, where the learning trajectories are a little more topical, but exist. Yeah. Would you agree or no?
We don't have the empirical data to support that, but I believe you're right. And one of the things about science is that there is a new conceptual framework for science that came out in 2012 that covers K-12 education. And we have moved that to a preschool-friendly version. So a lot of what that framework looks like, K-12, can be done in preschool, and we're now thinking about even toddlers and what the precursors might look like in infancy. But what the framework argues for is that science has to be learned by doing science. So there's a major focus on a set of scientific practices, things like asking questions, gathering information, making predictions, observations, and so forth. And preschoolers and even toddlers can do this, not clearly at the same sophisticated level as a 12th grader, but they can engage in these scientific practices. The second component of the framework refers to something called cross-cutting concepts. And the idea here is that there are certain truths about the world that also are relevant for math. Things like noticing patterns, paying attention to cause and effect relationships, looking for structure-function relationships, looking for how things fit together to create a system. And again, these are things that when you look at, preschoolers are exposed to. And then you have the content areas, and what the new framework has done is it's tried to reduce the content areas from 1,000 different things, because the prior education system just covered 9 weeks on hundreds of different topics, and the sort of view of students going through our system was that their science learning was a mile wide and an inch deep. So now we have the 4 content areas: life science, physical science, earth and space science, and now engineering and technology is a 4th piece of that, have anywhere from 2 to 4 big ideas. So the idea here is not to spread students learning thinly across lots and lots of topics, but to focus on a series of big ideas. So what we're trying to do is we're not so much telling preschool teachers you have to focus on this content, but rather follow the lead of the children, think about what the children are interested in. Typically there are projects that preschools do across the year. So if you plot out their calendar, they're engaged in a series of themes, which you can turn into nice projects. And then you can focus the teachers on using the practices, getting kids to engage in science and to do math as you're doing that. We include technology, we include engineering. But as Doug and Julie are pointing out, this is not something that is easy, and it's not something that's haphazard. You can't simply, let the kids do whatever they want, because they are excited about science. They love to count. They love the math. They love the science, but it's not intentional. And they'll flirt from one topic to another. So what we are doing with our teaching workforce is trying to get them to think about, as Doug and Julie are pointing out, what is it you want the kids to learn? And instead of just designing fun activities, and yes, activities should be fun, kids should have fun, but to think about, what are the children learning? How did you design an experience? What did you want to teach them? And how are you determining whether or not they're learning this or not? And across the year, the children will get exposed to a lot of the different content areas. And as that happens, we're trying to see, are there certain trajectories or certain things that should be learned first when you're learning life science or you're learning physical science? And I imagine those things are there, but we're not holding off and waiting. We're flying the plane as we're building it, because you can get kids are engaged in doing scientific practices, and if you make it intentional and teach them the routine, they have a question. Kids are question asking machines. They have thousands of questions. So if you said it as Doug was saying, don't tell them the answer. Help them discover the answer with their peers and with the teachers. And all these other things get added in. There's the social emotional, there's interacting, working with peers. There's a lot of language going on. There's math, there's creative arts, there's fine and gross motor coordination. So there's lots of advantages, as we were talking about, to making STEM something that's happening more often in early childhood. There's some sort of a perception that you have to stick to the basics. You have to teach kids foundational kinds of things. STEM is for later on. But these are what children are interested in, and these will form the foundations and the basics of learning. And as Doug and Julie point out, teaching kids to think, teaching them how to problem solve, teaching them these more complicated cognitive processes is, in the long run, serve them well as they move into the later grades, as opposed to rote learning.
Yeah, one quick addition, and then we're done, is that I really believe these local learning trajectories will be more and more prevalent as people like Daryl and the like keep doing the research. Just so you know, middle school, high school, it's a burgeoning field. They're in magnetism, magnetic forces and stuff like that. There are very well-developed kind of things. Unfortunately, we don't have as much in early childhood.
We'll get there.
We'll get there.
We'll get there.
All right, thank you very much for coming.
So.